So today we will be talking about Polya's theory of counting, or sometimes called Polya enumeration theorem. And first, just recall from group theory from last semester, given a group G and a set X, we define the left group action of G acting on X as the function, we can call it alpha from G cross X to some permutation in X, or we'll use it with permutations G cross X or G comma X becomes G acting on X, and alpha needs to satisfy for all HG in G and for all X in X. One is H acting on G acting on X is HG acting on X, and 2, the identity acting on any element, will keep that element the same. And just an example that will help us with our work with Polya theory, we can have a group G as the dihedral group for a square, and X is the set of vertices of the square. And if we took rho from D4 and we let rho equal 90-degree counter, or I want to do clockwise rotation, and if we have the square with vertices like this, rho acting on the square would be, here's the intermediate step, I'll just write, we can think of it as the vertices which relate to which. If we think of like permutations, 1 relates to 2, 2 relates to 3, 3 relates to 4, and 4 relates to 1. So we have 1, 2, 3, 4 with this orientation. So I'll also say that we'll want to use cycle notation as we do with permutations, where, for example, this is 1, 2, 3, 4, just the identity because the square is unchanged, and we end with 1 goes to 2, 2 goes to 3, 3 goes to 4, and 4 goes to 1. And Polya theory is going to be useful because we can look at cycle lengths, and we're also going to consider the orbits of different symmetries acting on the objects. So what Polya's theory helps us with is finding the number of distinct ways we can color different objects and considering different orders. Like having a necklace with 5 beads and 3 different colored beads. If we have blue, green, and purple, we could find how many distinct necklaces are made with 2 blue beads, 2 green beads, and 1 purple bead. Or you could switch the values. But Polya's theory will help us count how many necklaces we would have. And some terms before I get to the formula, we'll have the cycle monomial. So also if we can enumerate the beads. If we have some sigma in G, there's a corresponding sigma bar in X, the permutation, after G has acted on it. If like G, we would have the dihedral group of the pentagon for this one, and X is the set of the vertices. Then the cycle monomial is defined in this way. So Ci is the number of cycles of length I in sigma bar. So for this to make sense, we would have, if we go back to this original example, this would be 4 cycles of length 1, but this would be 1 cycle of length 4, or just Z4. Now that we have defined the cycle monomial, we'll define the cycle indicator as given here. This looks familiar because the fundamental idea here comes from Bornstein's lemma, which we use to count how many orbits we have under group action. And we do so by looking at how many elements in X are fixed by a given element in G. For our case of counting distinct necklaces, we count for a given symmetry of D5 how many necklaces will be the same if we account for rotating the necklace and turning it over in our hands, so the beads would be in the same place relative to each other. And we'll think of the different orbits as the distinct necklaces. So for the moment, I'm not going to consider the colors of the beads because we just want to look at the structure of the cycles after operating with each symmetry from D5. Also, R1, R2, R3, R4, R5 are just reflections through the corresponding vertex, and these are clockwise rotations since we go by 72 degrees. And we're just going to look at what the resulting cycle of the permutation would look like after acting on the necklace. So if we reflected through over the line going through vertex 1, 5 would go to 2, and 2 would go to 5. 3 would go to 4, and 4 would go to 3, and 1 would go to itself. So we'll write this later, but for now, for an example, I could write this is 2 cycles of length 2, and then 1 cycle of length 1. But we'll do the cycle monomials later. So this one, 3 would go to 1, 1 would go to 3, 5 would go to 4, 4 would go to 5, and 2 goes to itself. And I'm just going to fill the rest of these in. So now we have all the resultant permutations in cycle notation after operating on the necklaces. And we can go through and find the cycle monomial. So this would be, again, I'm going to do these in a different color. So I've gone through and written all the cycle monomials in light blue. So we have 4 instances of 2 cycles of length 2 with 1 cycle of length 1, and the identity 5 cycles of length 1, and then we have the remaining 4 symmetries produced 1 cycle of length 5 for each group action. So not much variation. So we can write the cycle index Z of Gx is 1 over D5. We know that's 10, but I'm just writing the formula. So we have this equals 1 over 10, and then we will sum all the cycle monomials. So we said we had 4 or 5 instances of Z2 squared Z1 plus 1 instance of 5 cycles of length 1 and 4 cycles of length 5. Now is when we consider the colors. And we say we have blue, green, and purple. So we're going to rewrite each Zi, replace it with B to the I plus G to the I plus P to the I. And this helps us add a weighted value to each cycle monomial. We'll have 1 over 10 times 5 times B squared plus G squared plus P squared to the second power times B plus G plus P plus B plus G plus P to the 5th power and plus 4 times b to the fifth plus g to the fifth plus p to the fifth. This is our weighted enumerator of g. And if we want to consider, now we'll consider the colors. Let's say we want to look at how many distinct necklaces there are made from 2 blue greens, 2 green beads, and 1 purple bead. And distinct, a necklace is distinct if it cannot be obtained by rotation from another. For example, if we had these 2 necklaces, they would not be considered distinct because all we did was toss this one around and flip it over in our hands and we got this necklace. So it's the same necklace essentially in a different position. And what we want to do to find the number of distinct necklaces made with 2 blue, 2 green, and 1 purple, we'll look for the coefficient on b squared g squared p in the above formula if we were to expand it, but we can do it in a more simplified manner. So considering the first piece, 5 times b squared plus g squared plus p squared all squared, we can think of it kind of combinatorically. So, oh, and I have this piece, b plus g plus p. So we can't get a p to the first from this piece. So we'll have to get it from this piece. So this gives us our purple bead. And then we have 2 of these. So there are 2 ways then to make the necklace. We could choose the 2 blue beads from here. B squared is here, but also g squared is here. And that would make us choose the green from here. Or we could do the opposite. So this is 5 times 2 different ways to make that necklace from this first piece in our equation. Then we have b plus g plus p all to the 5th. So if there are 5 of these, then we can think arbitrarily blue first, or without loss of generality. 5 choose 2 to choose the 2 blue ones, and then there are 3 choose 2 ways to choose green, and then the remaining one to get the 5th piece. That just leaves us purple, and that's just decided for us. So now we have 5 choose 2 times 3 choose 2 ways to get this necklace. And for the last piece, 4 times b to the 5th plus g to the 5th plus p to the 5th, they're all to the 5th power, so we can't get any necklace of this form from this or weighted cycle monomial. So this is going to be 0 ways. Our final step is summing this all together. We have 1 over 10 times, so we have 5 times 2 plus 3, 5 choose 2 times 3 times 2 plus, this is technically 4 times 0, which is equal to 1 over 10 is 10 plus 5 choose 2 is 10, and 3 choose 2 is 3. So this is equal to 1 over 10 times 40, which is 4. So there are 4 ways to make a necklace, 4 distinct necklaces with 2 blue beads, 2 green beads, and 1 purple bead. And here we have what the 4 different necklaces would look like.